All right, so as you can see, we're stepping on to the next thing as far as systems of linear equations. Last week we learned about solving by graphing, and we talked about the 3 different ways to solve them. Today you will learn the second way for solving systems of linear equations, which is substitution, and the name kind of tells you what you're going to do. Before we do that, I want to check your background knowledge with the old school Burger King logo. Remember when we talked about solving systems of linear equations, 3 different situations can come up. Basically, a system can have no solution. That, remember, was when lines were parallel, they never intersected, therefore they never had a solution, and that system was inconsistent. If they have one solution, that meant basically the lines aren't parallel. If they're not parallel, by definition, they have to intersect at exactly one point. That point is our solution, and that system was consistent and independent since those 2 lines were independent of each other. And then, of course, the last one, if you had the exact same line, you had infinitely many points of intersection and infinitely many solutions. So all this is review from last time, as well as this picture, kind of the visual aid to kind of tell you the different types of systems and different types of situations that can come up. That will still be true when we solve them using substitution as well as elimination. So just keep that in the back of your head as we go through solving these equations. To solve linear systems by substitution, some steps that you're going to look to. Step 1 is just going to be to solve one of the equations for one of the variables. Basically, you need to get it to the point where x equals something or y equals something. It doesn't necessarily matter which one's which, and sometimes they'll already be solved for you, but we need to get it so it's solved for one of the variables. You're going to use that information, and you're going to substitute whatever that expression is, whatever the expression x equals, into x in the other equation, or whatever y equals in for y in the other equation. And it'll make a little more sense when we get to the examples. But you have to take your expression and substitute it into the other equation for that variable. From there, you're going to actually substitute that value, and you're going to solve the value of that other variable. So there's going to be a couple substitutions. There's going to be the initial substitution of an expression, and then the second substitution of a number. And then, as always, like we've talked about in the past, you're going to want to check those values to make sure that they work. It might not make much sense now. Come back to this page in your notes, and I think it'll really make sense after you look at these examples. So first example says to solve this by substitution. You can see why maybe this wouldn't be the greatest situation to try to solve by graphing. You kind of have some ugly y-intercepts and ugly slopes and everything else. So what I'm going to do is I'm going to solve it by substitution. Now, as you can see, we actually already have one of these equations solved for y. This equation right here tells me that y equals negative x plus 5, or excuse me, negative x plus 15. I'm going to use that information, and I'm going to substitute that expression into the other equation for y, because they already told me what y equals. I know that y equals negative x plus 15. Now, I may not know what x is, but I do know that y relates to x in that way. My new equation on bottom then would become 4x plus 3, and now substituted in using parentheses, I would have 3 times a negative x plus 15, and all that would have to equal 38. So again, I've just taken whatever y equals, and I've substituted that in for y. Now I'm just going to clean this up and solve for x. So when I use the distributive property, I should see that 4x plus a negative 3x plus 45 equals 38. And now I can just solve from here. Combining like terms gives me x plus 45 equals 38. And when you solve for x, you should see that x equals negative 7. So as we get there, we're halfway to finding our ordered pair. We know that x equals negative 7. I'm now going to use that information back into the original equation. And now instead of substituting for y, I'm substituting in for x. We said y equals the opposite of x plus 15. Well, I know that x is negative 7. So y then would have to equal whatever the opposite of negative 7 plus 15 is, which in this case happens to be 22. And so y equals 22 and x equals negative 7. We come up with an ordered pair then of negative 7 comma 22 for our answer. Just to prove it to you real quickly, we'll check it in the second equation. So I want you to remember to go back to check these in both equations. I would have 4 times whatever x is, in this case negative 7, plus 3 times 22. I'm just checking it in the second equation to make sure that my ordered pair actually did work. I get a negative 28 plus a positive 66, which equals 38. And I check that and I say, hey, that absolutely is true. So it did work, and we do have one solution. That would be a consistent independent system with an intersection at negative 7 comma 22. Let's look at another example. This one takes a little more work. 2 equations, neither of them are actually solved for a variable yet, so that's what we're going to do. I noticed that if I just add 4y to both sides here, I now would have one of these actually solved for the other. I said x equals 4y plus 8. Remember, I'm going to take this piece of information and I'm going to substitute it in for x in the other equation. So now my new equation would be 2 times, and then in parentheses, 4y plus 8, substituting that expression in for x, minus 8y equals 6. I've just taken that and I've put it into the first equation. Now I know I can solve this. So I'm going to work this out. I'm going to use the distributive property again, get used to that with this type of problem. And I have 8y plus 16 minus 8y equals 6. I can combine like terms and I get to a situation where I have 16 equals 6. If you remember from your background knowledge, if our variables canceled out and we had a false statement, what was our answer? Just like before, in this case, we would have no solution. And so then I want you to think back to your notes and to what we talked about last week. How could we possibly have no solution? Well, remember, we said we would have no solution if the two lines were parallel. If they're parallel, they're never going to intersect and we're going to have no solution. If you look at both of these, you actually will have a slope of 1/4 on each one, and therefore, if they have a slope of 1/4 but a different y-intercept, you're going to have no solution because the lines are parallel. Last example. Again, we see that we don't have anything solved for a variable yet, so I just want to think about how I could do that. Give you the option as far as how to do that, but I'll tell you a tip from me. I think it'd be much easier if we could get rid of this fraction in the first one. You have y divided by 2 equals 2 minus x. I know to get rid of that 2, I'm going to multiply it by 2, but if I did that, I'd have to do that to everything over here. So my new equation would now become y equals 4 minus 2x. And now I've solved for y, and I can plug that in for y. So again, take this expression for whatever y is 4 minus 2x. Substitute that in for y in the other equation. That's the only way this works. And so now I have a new equation of 6x plus 3 times, in parentheses, 4 minus 2x, and that equals 12. Work this out using the distributive property. I have 6x plus 12 minus 6x equals 12. Again, we combine like terms and we say, all right, those are going to cancel out. Now we have a different situation. We have 12 equals 12. Again, background knowledge, back with one variable equations, we'd say all real numbers. Well, we can't say all real numbers necessarily because we're solving a system of equations. But if you think back to what we talked about, the situation that may come up is we may have infinitely many solutions if the lines are the exact same. If the lines are the exact same, then we can have infinitely many solutions. If you look at this, if you would solve both of those equations for y, get them into y equals form, both of these equations are actually the same thing as y equals a negative 2x plus 4. We do have the exact same line. And so remember, we'll have infinitely many, infinitely many solutions. And we have to be precise about what those are. So infinitely many ordered pairs. We have infinitely many solutions. And that's all ordered pairs on the line. And then you have to actually tell me what that line is. And in this case, it's y equals a negative 2x plus 4. Rather quickly going through the examples, but I think you see the idea. Remember, you're just going to take that expression for a variable, you're going to substitute it into the other equation, and then you're just using some algebra. You're solving some one-variable equations like back in the day. Again, the steps are right there for you in your notes, and we also spent a quick little time reviewing the different possibilities, but that really should take care of solving linear systems using substitution.